Good morning, students. Welcome back to the online classes, enrichment classes for standard 12th in physics. The next couple of classes will devote on learning the concepts of capacitors. In our regular classes, we have read about capacitors. Basically, we have discussed about parallel plate capacitor, whose capacitance we have derived as A epsilon naught upon D in vacuum. And if there is a dielectric inserted between the plates, the formula becomes A epsilon naught times dielectric constant of that medium, that is K upon D. We have also discussed the energy stored in the electric field between the plates of the capacitor is given by half QV or half CV square or Q square upon 2C. And we had also derived the relation for energy density. If you remember, energy density we have written it as small u, and that small u was energy per unit volume, and on calculation we get half times epsilon naught times square of E. Today, as I told, we'll discuss more on capacitors. Before beginning numericals, I'll discuss some more concepts. Today I will devote some time in discussing questions related to finding capacitance for different types of capacitors. You can see one heading I have given over here is spherical capacitors. Before discussing the method, let me generalize to you three important methods, three important steps which will be common for all questions. If you remember these three steps, it will be easy for you to write do the derivations. So step number 1. Whatever kind of capacitor is given, in between the plates of the capacitor, you have to find the electric field. Where you have to find electric field? Between the plates of capacitor. This is step 1. Then second step, after finding electric field E, you have to find potential difference between the plates. Potential difference between the plates. How will you find that? Potential difference between the two plates. You can write it as V is equal to V plus minus V minus, and that is given by the formula minus integration of E dot dr from one plate to the other plate. Means this lower potential plate to higher potential plate. And then third step, use Q is equal to C times V to find capacitance as Q by V. These are the three important steps. First find E, then use this formula minus integration E dot dr to find the potential difference V, and then use the formula Q is equal to CV to find C. With these steps in mind, let's proceed to our first topic today, that is spherical capacitor. In this kind of capacitor, we have two spherical cells. The inner one can be a cell or it can be a solid metallic conductor also, and the outer one has to be a cell. So these are the two plates. On the inner plate we will put some charge, suppose it is plus Q. On the outer plate we put some charge, say it is minus Q. So these two act as the plates of the capacitor. So this plate I will call it as plate A, this plate I will call it as plate B. They have a common center, and the radii of these two plates, you can take it as RA and RB, or R1 and R2 as per your wish. So I will write RA, radius of plate A, and this I will write as RB, center I will take as O. Okay, first step, you have to find electric field between the plates of the capacitor, that means in this region. In this region, choose any point. Let its distance be R from the center. To find electric field, we will use Gauss law. So we will draw the Gaussian surface in the form of a sphere passing through that point where you have to find the electric field. Now it is a symmetrical figure, so the electric field at this point must be in this direction. Let its representation be with E vector. From this point to this point, let this vector be R vector, Then a small displacement dr vector. Remember, dr vector is the vector directed along r in the direction of increasing r. Dr, you understand, I am telling its direction. In this figure, dr vector is radially outward. It is in the direction of increasing r. See here, r is increasing in this direction. So that is the direction of dr vector. So it is radially outward. Okay. So let's quickly apply Gauss law. So if we apply Gauss law on this Gaussian surface, the flux phi is integral E dot ds, and that you know it is equal to 1 by epsilon naught times q in. That is our Gauss law. Now this integral E dot ds will be how much? At all the points by symmetry, electric field has the same value. So this we have done such kinds of question earlier. So this becomes E into 4 pi this distance square, 4 pi small r square, and that will become equal to 1 by epsilon naught times charge inside this Gaussian surface. Inside this Gaussian surface there is charge plus q. So this gives our electric field as 1 by 4 pi epsilon naught q upon r square. Our step 1 is completed. And what about its direction? Radially outward. If yes, it is positive charge, so it will be radially outward. So these are the directions of electric field, like so. Radially outward. Here I have drawn like that. Next step is to find potential difference between the plates, that is V plus positive plate is B, so I'll write it as, I could have written VB minus VA. So this we know, minus integration E dot dr from this plate to this plate. Final minus initial, so initial to final. Initial is the negative plate. Negative plate is which one? This one, that is A. And this plate is B, is equal to, now E vector and dr vector we have discussed, they are directed radially outward. If they are directed radially outward, E dot dr will become how much? Simply E into dr, because cos 0 becomes 1, and integration will be from A to B. Instead of A to B, I will write, because the variable is R, I will write RA to RB. Now this can easily be simplified. To put the value of E, this much. So 1 by 4 pi epsilon naught will come out, Q will come out, and what will be left? 1 by R square times dr from RA to RB, and there is a negative sign. Is it clear, students? Now what is 1 by R square dr integration? That is minus 1 by R. That minus and this minus will become plus. So you will have 1 by 4 pi epsilon naught Q 1 by R, the limits of integration from RA to RB. So therefore V is equal to how much? 1 by 4 pi epsilon naught Q into 1 by RB minus 1 by RA. Our step number 2 is finished, and at last we will use step number 3. What is step number 3? Our step number 3 is to find capacitance using the formula Q upon V. Q upon V, from this formula we can see, will become how much? 4 pi epsilon naught. One more step I can write here. This is, you can take LCM, Q upon 4 pi epsilon naught. I am writing here only, no problem, RA into RB, and LCM, after taking LCM we will get here RA minus RB. So C is Q by V, so Q upon V will be 4 pi epsilon naught multiplied by the product of RA and RB and divided by RA minus RB. So this is our formula for the net capacitance of a spherical capacitor. Is it clear, students? Let's see a special case for this. A single sphere isolated, whether it's spherical cell or a sphere, solid sphere, is also a capacitor. Now you might ask, where is the second plate? We assume in this case that the second plate is at infinity, very far from the first plate. So this is also like a capacitor, remember. And in this equation, if you put Ra and Rb as these radius, so one of the radius becomes infinity and other radius becomes capital R. Our previous figure was like this. This was A, this was B, so this is Ra and this is Rb. In this case, the second capacitor is spherical capacitor. I am discussing that it is at infinity, very far from the first plate B. So Ra we will set as infinity and Rb we will set as R. If you set these two values, we will get the capacitance for an isolated sphere. So remember, if we have a spherical object, conducting object, and if you charge it, it behaves as a capacitor. So what will be the formula for capacitance? Capacitance will be this one. So 4 pi epsilon naught. Ra is infinity. What I will do? Ra I will divide in numerator and denominator. So this becomes 1 minus Rb upon Ra. Just to deal with infinity. Now you put Rb is equal to how much? Capital R. Rb I will put as capital R and Ra I will put as infinity. Now R by infinity tends to 0. So how much will be left? 4 pi epsilon naught into R. This is the capacitance of a single isolated sphere. This you can arrive at this particular result using another method also. We know that the potential at the surface of a spherical conductor V is given as 1 by 4 pi epsilon naught times Q upon R. You know this, students. If you know this relation between V and Q, you also know the capacitance, because capacitance will be given by Q upon V. So Q upon V from this relation you can see becomes how much? 4 pi epsilon naught times R. So both these results are same. So this is all about spherical capacitor that I wanted to discuss. Let's see some more types of capacitors. Next you can see we will discuss about cylindrical capacitors. So instead of spheres, it will have cylindrical shaped plates, as you can see on the screen, on the board. Now this derivation which we shall do, that will do on the basis of one assumption that the length of the cylinder is large. It is long cylinder. Large compared to what? Compared to this separation between the plates. So inner plate charge plus Q, outer plate charge minus Q, radius R1 and R2. So R2 is greater than R1. First step, you have to find electric field. For electric field, we have to draw Gaussian surface. By symmetry at all the points on the cylindrical Gaussian surface will be same. So this is our Gaussian surface in the form of cylinder, and all these three cylinders have the common axis through center. Clear? So this is the axis. Should be drawn through the center like so. So this is axis, common axis for all of them. And this cylindrical surface which we will take as Gaussian surface, we have drawn it at some distance, say small r. And we assume its length to be something, say it can be anything, x. You can take some other variable also. The first step is to find electric field. So how do we find electric field? We will use the concept of a flux. So first let's see how much will be flux. Flux is integral E dot ds. Now by symmetry, electric field at this point must be directed radially. ds vector is also directed in same direction. So E and ds are in same direction. So we get E into ds. But E at all the points on this curved surface will be same. So E you can take out, and this curved surface area becomes how much? Perimeter of base into height. Perimeter of base will be 2 pi into this radius, that is r, and into height. Height is how much? X. Is this step clear, students? At all the points on the lateral surface of the cylinder, electric field has same value, so it will come out of the integration. We will be left with integral ds, this one. Curved surface area of a cylinder is 2 pi rx, where x is the length. Remaining two faces of the Gaussian surface do not contribute to flux because the area vector will be like this, here the area vector will be like this, and these two vectors are perpendicular to the direction of electric field, so E dot ds vector will become 0. So this is our flux. Now flux is how much? 1 by epsilon naught times q in. So this implies this is equal to 1 by epsilon naught times q in, charge inside the Gaussian surface. Inside this Gaussian surface, the charge is present in this much portion of the cylinder. Now for length L of the cylinder, the charge on this cylinder was how much? Plus q. So on unit length, what will be the charge? Q upon L. What is the length we are considering? We are considering length x. So on it the charge will be q by L times x. So these two flux we should equate. So therefore E into 2 pi Rx must be equal to Qx upon epsilon naught times L. So x will cancel. This will give you the value of electric field. E is equal to Q upon 2 pi epsilon naught R times L. Is it clear, students? So this gives us the value of electric field, Q by 2 pi epsilon naught RL. Next step would be to find potential difference between the plates of the capacitor. How will you find that? We will find that by simply using the formula, this one. So V is equal to V plus minus V minus, and that is equal to how much? Minus integration E dot dr from minus plate to the plus plate. Negative plate is which one? That is having radius R2. So R2 to R1. Now E and dr vector are in same direction, these things you know. So E dot dr will become simply E into dr, and E is constant, so E will come out. Sorry, E is not constant, it depends upon R. So this becomes minus integration from R2 to R1. E value will put Q upon 2 pi epsilon naught RL, then dr, and then cos 0 degree, cos 0 becomes 1. So this becomes, take the constants out, 2 pi epsilon naught L, and this Q will come out. We will be left with integration dr upon R from R2 to R1, and there is a negative sign. What is integration dr by R? Integration dr by R is ln R, log R. So let's put the value. Our V will become minus Q upon 2 pi epsilon naught L ln R, and the limits will be from R2 to R1. So what will we get here? ln R1 minus ln R2. ln R1 minus ln R2. Now take this minus sign inside, so this will be flipping, this will flip, it will become ln R2 minus ln R1. Log A minus log B, you know students, what is the value? Log of A by B. So here it will become R2 by R1. So ln R2 upon R1. This is our potential difference. So this is our second step. At last now we will have third step. Third step says Q is equal to CV. So therefore capacitance will be Q upon V. Now Q upon V will be how much? 2 pi epsilon naught L divided by ln R2 upon R1. So I would suggest you to please do the derivation again, but the basic steps are these three steps. Whatever be the nature of capacitor given in the question, follow these three steps, you would be able to do the derivations. Okay. Having understood how do we deal with finding capacitances for some special types of capacitors, next I will begin with discussing finding equivalent capacitance. You already know how do we calculate the equivalent capacitance in case of series or in case of parallel or both kinds of combinations. What you know is this. So these two are in parallel, you know. So C2 and C3 are in parallel, and that combination is in series with this particular capacitor C1. So to find capacitance between A and B, first we see that these two are in parallel and their equivalent capacitance will be how much? C2 plus C3. So C1 is in series with their combination will be how much? C2 plus C3, because they are connected in parallel. So this point is B, this point is A, and therefore the net capacitance, now they are in series, so net capacitance, suppose it is CAB, so 1 by CAB is equal to 1 by C1 plus 1 by C2 plus C3. Now this can be written like so, C1 times C2 plus C3, and then we'll have C2 plus C3 plus C1, and therefore the equivalent capacitance between points A and B will be C1 times C2 plus C3 divided by C1 plus C2 plus C3. So this is the way is to find equivalent capacitance between the points A and B, but I will discuss one more way to do it, and that is a general method. See students, it's not necessary that in a particular question the given capacitors would be necessarily in series or in parallel. In this it is okay, so this method is better, okay, you have done it. What I am going to discuss now is a general method and will be applicable for any kind of combination. I have chosen a simple example just to make you understand better. Step number 1 is to join the 2 points between which you have to find the capacitance to an imaginary battery. Think in your mind about some imaginary battery connected between the 2 points between which you have to find the capacitance. The positive end of the battery will send some charge, suppose it is plus Q, to one side, and minus Q it will send to the other side. Just you have to think in mind. So if this is plus Q, you know this right plate will have charge minus Q, and then this plus Q will distribute itself into these two. Out of Q, suppose Q1 goes here, out of Q, if Q1 goes here, remaining will be Q minus Q1. So this will be how much? Minus Q1. This will be negative of this, that is minus of Q minus Q1, and you can see that this plus this must be equal to this. You can check it out. Minus Q1, so probably it's not visible, so let me write it a bit below. So minus Q1 and minus of Q minus Q1. So this minus and this minus becomes plus. So plus Q1 and minus Q1 cancels. Minus Q is left. Likewise, this plus this should be equal to this. You can see Q1 and minus Q1 will cancel. This is Q. Q is the charge on this capacitor. The trick to distribute the charges is that you concentrate on this combination of plates. Before the battery is connected, this and these 3 plates of the 3 capacitors, the total charge was 0. Law of conservation of charge says there should be net 0 charge always on these 3 plates together. If you sum them up, so minus Q plus Q cancels, plus Q1 minus Q1 cancels. That is the trick, students, remember that. Always the sum of the charges on this and this will be 0. You can see this is an isolated system. Inside this blue boundary, whatever thing I have drawn, that is an isolated system, that is not connected to the rest part of the world directly. You can see there is a gap, there is a gap, there is a gap. So charge will flow between themselves only. Net charge was 0 initially, so finally also net charge must be 0. After understanding the charge distribution, we will proceed further to find the equivalent capacitance. For that, again second important thing, the imaginary battery which we have connected, it will have some potential difference, say V. This is at higher potential, this is at lower potential. So this one you assume at 0 volts, the higher potential you take it as V volts. Now the connecting wires, they will not have any potential difference. All the points you should take it as to have same potential. That is the definition for equipotential surface. Conductors are equipotential. So in a static situation, if this point has potential V, all these points will have potential how much? V. Likewise, all these points would have potential 0. So this is 0, 0. These are the 0 volts. These points will have same potential, but that is not known. Let that potential be V1. All these points, this point, this point, this point, this point, they have potential V1. So potential difference across the plates of capacitor C1 will be how much? V minus V1. Across capacitor C2, it will be how much? This potential minus this potential. This is at potential V1, this is at potential 0. So this potential will be V1. Likewise, this potential difference will be how much? This minus this. So this minus this means V1 minus 0, that is V1. So on each capacitor, now we know the charges. We also know what is the potential difference. So we can use the formula Q is equal to C times V, and we can frame some equations. So let's see what equations we get. For capacitor C1, for capacitor C2, for capacitor C3, let's write the equations. Charge is how much? Q on this capacitor. Capacitance is C1, potential difference is V minus V1. That's it. On capacitor 2, what is the charge? Charge is Q1. See students, you might feel that this was much easier. It's not the question of easy and difficult, it's the question of method. In this particular question, of course, you might feel in the beginning that this is an easy method, but there are questions wherein you cannot solve such questions by this method, simply because the capacitors may not be in series, may not be in parallel. It is possible to have a combination where the capacitors are neither in series nor in parallel. There this method won't work, this will work. So it's important to learn the method. So Q1 will be how much? Capacitance C2 into potential difference V1 minus 0, that is V1. And for third capacitor, Q3 will become, not Q3, the charge is Q minus Q1 and capacitance is C3, potential difference is V1. So we have got three equations, 1, 2 and 3. We have to solve these equations to find net capacitance. By the way, the total potential difference is V. Total charge that we sent was plus Q and minus Q from the opposite poles of the battery, that means Q, and total capacitance of this combination is suppose C. Then we must have Q is equal to C times V, or C is equal to Q upon V. So we want Q and V relation. Q is there, V is also there. What is unwanted is this V1. So we have to eliminate V1 and we also have to eliminate Q1. So what we can do to eliminate Q1, we can add 2 and 3. 2 plus 3 if we will do, Q1 and minus Q1 will cancel. So we will be left with Q, and here we will have C2 plus C3 whole into V1, and this will give you the value for V1. So V1 is how much? Q upon C2 plus C3. Put this value of V1 in equation 1. So Q is equal to C1 times V minus V1, that is Q upon C2 plus C3. Now we have to rearrange the terms and we have to obtain a relation between Q and V. So terms containing Q will put together. So this I can write as, I will open the bracket, it will become C1 into V minus C1 into this much. This I will take that side, so Q will be common. What will be left? 1 plus C1 upon C2 plus C3, and that will become equal to how much? C1 times V. Is it okay? Here we will take LCM. C2 plus C3, and this will become C2 plus C3 plus C1. You can arrange and write C1 plus C2 plus C3, and that becomes equal to C1 times V, and therefore our capacitance C, which is Q upon V, will become equal to how much? Q upon V, you can see. So this is C1 will come in denominator, it becomes C2 plus or C1 plus C2 plus C3 divided by this into C1, that is C1 into C2 plus C3. We have got some reciprocal. Let me check it out. Of course, this is wrong. It will be reciprocal of this. So C is Q upon V, Q upon V, this will go here. So C1 into C2 plus C3 divided by C1 plus C2 plus C3. So this is the answer to this particular question. So as I told students, please understand how I discussed this particular method, and you will utilize such methods, such concepts in further questions. So today was basically an introductory to the enrichment class on this topic of capacitors. Next class we will use these concepts. Please revise this concept properly and come prepared in the next class. So till then, take care, or take very good care of your health, study well, all the best.